As the integration becomes higher and higher, the power densities inside our devices continue to grow. This heat has to be let out from the devices to maintain reliable operation. The thermal interface materials play a significant role in the heat conduction path. More than half of the total thermal resistance of the thermal assembly may depend on them. They act as thermal bottlenecks of the heat flow path from the semiconductor to the external cooling assemblies. Team 1 type materials conduct the heat from the silicon chip to the package base, and Team 2 materials allow proper thermal contact between the package and the cold plate. Thermal interface materials consist of thermally good conductive microfillers. In reality, the teams don't ideally conform to the material surfaces, which result in an increased contact resistance. The sum of the contact resistances and the resistance of the team give the total performance of the interface. In order to reduce the thermal resistance of the team materials, the partners of the NANOPACK consortium applied the latest advances of the nanotechnology. Polymer metal composites are also good candidates to enhance the conductivity of the teams while establishing good mechanical stability. In ideal conditions, they fill up the voids and surface inequalities between the two contacting materials, and the microfillers squeeze to each other to allow the heat to easily pass through the interface, eliminating the thermal bottlenecks. A new technological approach to reduce thermal interface resistance in die bonding is the so-called nanosponge. It is made of a highly conductive pure metal harboring pores of the size of a few 10 nanometers. These pores render the nanosponge very compliant. Carbon nanotubes have been shown to possess intrinsically extremely good thermal performances, such as a thermal conductivity as large as 3000 watt per meter Kelvin in some cases. In NANOPACK, Teles Research and Technology investigated the crucial issues of the growth of dense areas of vertically aligned carbon nanotubes from bottom substrates, the infiltration of diverse materials between the tubes, as well as the connection to the top substrates. At the contact between nano or micro particles, the heat carriers, usually phonons or electrons, can indeed be reflected due to bad nanometer scale adhesion or simply to the mismatch in acoustic or electronic properties. Surface functionalization allows improving the heat transmission, for example via its nanostructuration. To describe the heat transmission at the surfaces, the physics of thermal transport phenomena is required. It enables to discover ways to accord the phenon spectra of the different materials and to calculate the reflection at the boundaries. Due to the difficulty in analyzing the complex thermal interface materials, a set of different techniques has to be used and especially developed. Measurement techniques of thermal properties are indeed known for being much less accurate than those of properties such as electrical ones. A very detailed benchmark of different thermal techniques was performed in the frame of the project. It consisted in the comparison of reliable techniques that measured the team performances at the chip scale. In situ measurements were performed on large ranges of surfaces, silicon, copper, silver, and lots of other ones, and thicknesses. In some cases, the interface thickness is below 10 micrometers. Major achievements of NANOPACK are development of high-performance teams and process, development of CNT bumps for microfluid teeth, development of accurate team characterization tools, modeling and simulations, and application to demonstrators for several industries.